Okay, so you have got your value for row. Now, I'm talking about the errors in sort of one go. I'm going to do it in a couple of hits, but I'm talking about them together. But in actual fact, you might, as I suggested in the previous video, you might actually want to talk about the first errors bit and do that before you plot the graph, because working out the errors initially can actually help you. So, error calculations up to graph. Okay. Right. Effectively, the end game for this bit is to get error bars. And also an error in A, because you're going to need the error bars to take errors into account on your graph, and you're going to need the error in A because you're going to have to calculate something from that. So, essentially, every calculation you do, you need to do the equivalent error calculation. So what calculations have we done? We've worked out mean V. Probably mean I as well, but except that most of you probably have only done repeat readings of V. Mean V, you've worked out resistance. Essentially you've converted length to meters. That's not a massive calculation, but we do need to think about that in terms of what that means for the errors. But that's really just, you just do a unit conversion on those. That is easy. You've done mean diameter, and you have calculated area. Okay, so the first and third are going to lead to error bars, and the second is sort of separate. You're just going to need that for after you've plotted the graph. So again, I'm just going to split these off into little notes at the side. 1. You need to work out the standard deviation in your repeat readings. Have a little look back at the error notes before that. You can look up the equation for it. Just Google the equation for it. It's basically just difference between value and the mean. Difference between value and the mean. Difference between value and the mean. Squared, add them all together, divide by how many you've got, square root. But work out a standard deviation for each set of repeat readings. So, for each length. So, at 20 centimetres, you took 3 or 5, hopefully 5 is better, 5 potential differences. 5 values for V. You want the standard deviation in those. In the next column in your table, you want the standard deviation in those sets of repeats. It's not the standard deviation in a table, in a column, that would make no sense. Alright, it's in each row as you go. You then want to work out from that what the standard error is. So this is nice and easy. This is just taking the standard deviation. And just to remind you again, you've got the examples of where I did the calculations for the pendulum experiment. So you need an exemplar for each one of these as well, remember. Again, every type of calculation needs just one exemplar. So here, for example, we were calculating the 20 oscillations in a pendulum. And we did that as repeat readings. So we work out the standard deviation for each set of repeat readings for a length of pendulum. So I've written the equation in. So just bear in mind that this, and it's the same for the one that you're doing now. If I can zoom in a little bit on that. You're using obviously the sum of the distance and the means, but it's divided by n-1 because it's a sample basically. Because it's a small sample, you lose that for big samples because it doesn't make much difference. But you divide it by n-1 and then square root the whole thing as well. It's not just the differences that get square rooted. So that gives you a standard deviation. Then if you divide that, so down here marked up as equation 3, the standard error is the standard deviation divided by root n. So, I'm not writing the standard deviation equation out, but standard error is the standard deviation divided by root n, which is the number of repeats. So you get the standard deviation in the repeats, and then divide that. So if you've got 3 repeats, get the standard deviation in the 3 repeats, and divide that by root 3. Okay, that gives you your error in v. So that gives delta v. So that's the notation we use. So this gives delta v, which is what we mean as error in v. Okay, and you need to do that again. I'll say this really explicitly. Do it for every set of repeats. So what you'll notice in the example lab diary is I've put these in a table. So I've got the error in each one kind of recorded somewhere. And I've got the calculations of the means, the calculations of the standard deviations, they're all there. Alright? So you basically want, in the same way that I've done the trials here, you want an error in V written down in its own column. Okay? If you've done the same thing for current, then you'll need to do the same here for current as well. But if you've just got like raw data, or only recorded the current once, then that's fine. Ideally you would do multiples, but it's fine if you've not. But put the errors and then the standard deviations and then the standard errors. Most importantly, you want the standard error in its own column, because you're going to need that in a minute. Okay? Right. Moving on to number 2. How do we then get the error in the value for R? Right, so you've got to look at how you calculated it. Oh, sorry, no, there's one more thing. If your 3 repeat readings are the same, then you're going to get an error which is 0. Now, nothing has an error of 0. If that is what it's going to come out at, then use the original error from raw data. In other words, the 0.00 plus or minus 0.005 volts. Just use that. Okay, if you're going to get 0, you cannot have a 0 error. So use the original from the raw data. You can see that quite clearly, because if you look at your data and you go, well, all 3 of these are the same, I'm going to get a 0 standard deviation and 0 standard error. You don't need to calculate it. Save yourself the time. But please don't ignore that. Remember, you are being assessed potentially on this. So you probably should just put a little note to say, standard deviations come out, the repeat readings are the same, so the standard deviations are the same. So the standard error is the same. So the original raw data error has been used. Boom. Look, I know what I'm talking about. That's what you want to say. That's the idea you've got to get across. Okay, so then you're going to use that to get the error in R. So how do we get the delta R? Right, look at what you did to calculate R in the first place. V over I. That means that R is a combination of the error from V and the error from I. Right, let's just have a little look at a results table. Now, in this results table, it's a bit of an excerpt, and I might not have all these in the same table, but just for ease. I've got my mean value of V, and I've got my error in V, and I've got my raw data for I, and this is plus or minus 0.005, and all that's in amps, and all these are in volts. And then I'll have my calculated value for R. Again, no plus or minus because it's not raw data. And that would be in ohms. But here, I'd have delta R, again, in ohms. So what I end up with is my calculated values of R, and right next to that is my error in R, and that's what I'm going to need. It makes sense to put them together, but they don't have to be. Right, let's just go through a quick idea of an example then. So let's say that this was 1.10, and let's say I've had to use the original raw data, so 0.005. Let's say my current is 0.80, and again I'm using the error at the top of 0.005. So my resistance would be, if I work it out for that, V divided by I, so 1.1 over 0.8 is 1.375. Well, I can only really go to two significant figures, so I'm just going to go for 1.4 with that. So what I need then is to work out the error in that value. Okay, so what I need is the absolute error. I need the error in ohms. And to do that, I need to get the percentage error in R, which is the percentage error in V plus the percentage error in I. And this is why errors take such a long time to do, because you've got to calculate now each one of these. So it might make sense to go, okay, what's my percentage error in I? You don't have to have it in the table, but you know what? It doesn't have to make life easier if you just leave it in the table. What's my percentage error in I? I'll do V first then. So that would be 0.005 divided by 1.1 times 100 equals, go on, what would that give me? 0.45%. So my error in V is 0.45. Likewise for current, percentage error in current. I'm using the plus or minus because this was raw data, so I'm probably going to have the same thing for everything, 0.005. Whether the V error is the same for every one of them would depend on the repeat readings, so it might get a different value for every one of those. Over 0.8 times 100, 0.005 over 0.8 times 100. That gives me 0.625, so 0.63%. So squeeze that in there, 0.63%. Right, so then go back to, I want the percentage error in R is 0.45 add 0.63, so 0.45 or 0.63 gives me 1.08% error. Now I don't want to put that in there because I don't need it in a percentage, I want it in ohms. So I've got to go back to my original value, which was 1.4. So get the absolute error. So I want 1.08% of my 1.4 up there. So 1.08 out of 100 times 1.4. 1.08 out of 100 times 1.4 gives me an error of 0.01512. Right, so there's no point me going to loads more significant figures than I've got. So my error in R, well, I'm going to have to go to an extra, otherwise I'm going to have to ignore it, aren't I? So 0.02, I'm going to have to go to 0.02. So now I've got an error in that value of R. Now it's a bit long-winded, alright, it doesn't take forever, but it does take a bit of number crunching. You've got to do that now for every row in the table. Okay? So if you've got 6 different lengths, you need to work out a value of R and the error in R for each of those different lengths. How you then fit this in with the graph is when you come to plot that point, so this is plus or minus and that many ohms, volts, idiot, that many ohms, would plot the point of R at 1.4. Wouldn't necessarily have 1.4 on the axis, you understand. But I would do a plus or minus, where I'd go a little I up and a little I down, up by 0.01, 0.02, down by 0.02. Now you might find that that's too small, okay? But it doesn't matter, work them out for every one of them. So every one of your points needs an error bar. Bump, 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 bump. And there'll be different sizes. Don't work out this one and assume it's going to be the same. The percentage is going to be different from V and I because the values of V and I might change. So the percentage in R is going to change, and as the value of R has changed and the percentage of R has changed, you're going to get a different error for every value of R. You need to work it out separately. There's no shortcuts, I'm afraid, with this. But if, by the end of it, the error bars are too small for the graph, and by don't show up, I don't mean that you wrote them in too fine a pencil so I can't see them. What I mean is if they don't show up, they're too small. Then, instead, pick the largest and write it on the axes. So you might, for example, where you've got R, you'd have ohms, you might include a plus or minus 0.02, or whatever the largest would be. Okay? And then you don't need error bars, because they wouldn't show up. So if your errors are too small to show up on the graph, you can still put them on the graph, but put the worst case scenario as a plus or minus on the axis label, and don't put error bars in. Okay, so that's the long-winded bit. Convert L to meters. Alright, well that's easy. But remember, 3. Convert the error to. That's the only thing with that one. If yours are, 1 centimetre plus or minus half a centimetre or something like that, then you need to convert both of those to meters. And plot an x-axis error bar. So ideally, what a graph would look like, if it can have two error bars, is it would do like that, it'd have a few points on it, and then for each point, you would have a y error and an x error. But obviously the same applies. In this case, because L was raw data, all of your x bars are going to be exactly the same. So that does make life a little bit easier. You don't need to calculate a separate one for them. But the same rule applies. If they are too small, then you write it on the x-axis instead. But please make sure it is too small. If it would show up on the graph, you need to put it on the graph. So if it's too small, plot it as a plus or minus in there as well. And it needs to be in matching units. Okay, so that gets you up to the point of having error bars on the graph. So that's the first part. It's a nice idea sometimes to do all the processing, get to the point where you're ready to plot the graph, then do all the processing of errors, and then get everything to that point, all your data to this point, and then plot the graph. Okay, and I'll talk about next what you do with the final errors. This is harder work, the next bit is a lot easier.